What's up? This is Investigating Diffusion. You're probably wondering, what is diffusion? Diffusion can be defined by the tendency of molecules to spread out in order to occupy an available space. And as observed in this animation, molecules in a solution have a tendency to diffuse from a more concentrated environment to a less concentrated environment. This is a spontaneous process, which can be explained by kinematics using velocity, position, and acceleration.
In previous labs, we have explored the motion of objects moving in one direction. We've done this by utilizing ILabs. Now we're going to be adding another dimension to our model. And by doing so, we're going to be able to look at the displacement of the particles and calculate their velocity when they diffuse in solution.
The purpose of this lab is to characterize the random motion of beads suspended in a solution and determine how their variation of experimental parameters impacts the movements of beads and their resulting diffusion.
Here's a list of all the materials that we use. And the solutions that we tested were water, soap, and cornstarch in order to study the motion of microscopic beads and fluid under a microscope. Using previous background, we found that the cornstarch has a molecular weight of 692.6, water with 18.02, and soap with 306.97.
This is the procedure we utilize to collect our data. Here, as you can see, we decided to set our calibration sticks for X and Y to 1 meter each. We did this so that we can collect the qualitative data for velocity, looking at our reproduced data and graphs. Another thing that we decided to do as a group is to collect 2 sets of videos per solution in order to have more accurate data.
As mentioned before, our group used Tracker to measure 2 individual beads per solution, and we did this to create more accurate data. And after tracking it using a 20-second duration, so about 40 frames per video, we transferred the X and Y position data into an Excel and therefore outputted graphs for each solution. As presented here, these are the X position graphs for water. Here are the X position graphs for 2 individual beads in cornstarch. And lastly, we have the X position graphs for 2 beads in soap.
We use these calculations to solve for the velocity in both the X and Y directions, and then using that we use the Pythagorean theorem to find the average velocity of each of the beads.
The following table presents the solution velocities for water, soap, and cornstarch, and it shows the calculated velocity for bead 1 and bead 2, because as we said before, we're going to measure the position and time for both of them. We use these calculated velocities and average them out in order to have one average velocity per solution.
Using the average velocities, we have created a bar graph to demonstrate how the velocity in each solutions vary, and we have found that the velocity in water is much faster than the velocity in soap, which is also much faster than the velocity of cornstarch.
From doing this lab, we can define random motion as particles moving independently without a predictable pattern. Even though this movement is random, we have noticed that by changing parameters, we can affect motion. For example, changing the solution, which is what we did in this lab. The motion of the beads can be described as random and independent from each individual bead in solution. Diffusion in this model is represented by the movement caused by collisions between the beads and the molecules of the surrounding liquid. Therefore, by changing the solution, we are changing the mass of the surrounding liquid. Thus, we're increasing the viscosity of the solvent, and this influences the transitional and rotational motion of a molecule in solution. In other words, the more viscous the solution, the slower the beads will move. The bigger the mass of the molecules in solution, the slower the beads will move.
Through analysis, we have observed that the beads in water move faster than the beads in soap, which move faster than the beads in cornstarch. Therefore, we can conclude that by changing solutions, we change the mass of the molecules in solution, and the bigger the mass, the harder it is for the beads to travel.
In the computation model, the particles were the proteins in the solution, and to emulate this in our investigation, we use beads in the different solutions to represent the proteins. The investigation accounted for gravity, whereas the computational model did not. When the beads first dropped into the glass slide, that is when they have the fastest movement. The delayed reaction time can contribute to an error that calculated velocity. Also, some beads were moving so fast that we could not track them because they went out of view. Therefore, we had to analyze the slower beads that remained in view. The beads were so small that we couldn't analyze them as precise as we wanted to.